All right. So like I was saying here, guys. Oh, there you go. Okay. So like I was saying, today we're going to go over position versus time and velocity versus time graphs. Okay, we're going to learn what we can read off of each one, how we can infer what's happening. Okay, what things we can calculate from each type of graph. Okay, all of that kind of stuff. Hopefully that's all going to seem very familiar to everybody because we are going to move pretty quickly today. Okay. All right. So first thing we want to talk about is position versus time graphs. All right. What can I read directly off of a position versus time graph? Spoiler alert, I may have already given it away. What are the two things that are on a position versus time graph? Position and time. Okay, I can tell from a position versus time graph where an object is at various points in time. Okay, so I can always read that. From that, I can infer a few things based on the pattern I see on the graph. I can tell whether an object is moving at a constant velocity, or whether an object is accelerating, or whether it's moving forwards, or whether it's moving backwards. Okay, based on where the points go and where the points are. Okay, everyone follow me there. All right, so as an example then, okay, if I have this graph here, in this first part of the graph, so right here, I've got just a straight diagonal line. Okay. Now, according to that diagram there, it says that that means the object is traveling at a uniform or constant velocity of 180 kilometers per hour. Okay? If that's a uniform velocity, what are they missing off of that 180 kilometers per hour? Direction. Okay? It doesn't really say direction on this graph, and it really should. All it's got here is negative and positive. So, well, we should probably put a positive beside that. Okay? Now, since the graph is a straight line, how do I know that means the object is traveling at a constant velocity? Why does a diagonal line tell me that? If a line is diagonal, like this, does it go up the same amount it goes over every single time? Okay? Does that mean that on this graph, it changes its position, the vertical part, by the same amount for every unit of horizontal movement? Right? So every second, does it go the same amount it went the second before? And the second before that, and the second before that. It does. Okay? If you've got a diagonal line on any type of graph, it means that y is changing at a constant rate over x. In this case, it's in position and time. So its position in kilometers is changing at a uniform rate per hour. Kilometers per hour. Okay, everyone all right with that idea? Okay, now, after that, the line starts to do this, and it curves until it's flat. Okay? And on the diagram, it tells us that that means it's decelerating, which is not a word we like to use in physics. Okay? But it's on there. Okay? We prefer an acceleration in a negative direction, but decelerate will do for now. Okay? How do I know that that curve means it's slowing down?
It's traveling less for every unit of time.
Yeah, it travels less far for every unit of time. Okay, so here's 0.1 hours. Okay, from here to here represents 0.1 hours. That is how far it went in that 0.1 hours. In the next 0.1 hours, it only goes that far. Is that less than here? Okay, that line is shorter, right? That vertical line is shorter. Right? If I was to, really amplify that graph so it looked kind of like this, it would be like, okay, here it went really far, and the next one not quite as far, and in the next one not quite as far again. You can see that that horizontal line or that vertical line, sorry, is getting shorter and shorter every single time interval. Okay? And the only way it can not travel as far in the same amount of time is to be going slower. Okay, everyone all right with that idea? So that's an easy thing that I can put in a multiple choice question on the unit exam. Okay, here's a graph. Tell me what's happening on the graph, A, B, C, or D. Okay, object is standing still, object is accelerating, object is slowing down, object is moving at a constant velocity backwards, okay, or something like that. And you'd have to pick the right one. Okay, all right. Here it says the object is stopped. How do I know that?
The position is constant.
Right, the position is constant, it's at 0. Okay, it's at the station, it's not moving, okay? There's no vertical movement of the points on the graph, right? That means the position's not changing. If your position's not changing, then you're not going anywhere, okay? Then in this part of the graph, it says it's accelerating. Okay? And that kind of fits. It's the opposite of what we said over here. Okay? In this 0.1 hours, it went that far. And then in this 0.1 hours, it went that far. Much further. Okay? And then in this 0.1 hours, it went even further. Okay? Yeah, it's definitely accelerating. Okay? And then after that, we have a diagonal line again that says it's traveling at a constant velocity. Okay? This is definitely not a train from around here. Okay? Our trains don't go that fast. If you go to Europe, you can get on the bullet trains that do go that fast. Okay? All right, is that making some sense? All right, so that's how I read a position versus time graph. I can look at it and I can tell these things from certain patterns. I don't have to memorize those patterns. Okay? I can look at the graph and do exactly what I did here. Okay, in 1.1 hours it went this far, in the next 0.1 hours it went that far. Well, that means it's got to be going faster. Okay, I don't have to memorize it, I can just analyze it. Right? And that's what we want you to do, is learn how to analyze graphs. Because in physics 20, you're going to have like 4 or 5 graphs. Okay? But physics 30, like 25. Okay? At least 24 different graphs. Can you memorize what every little thing is on 25 different graphs? If that's the only thing you have to do, maybe. Okay? But you're bound to get something wrong. Whereas if you have the ability to analyze a graph, you can use that on any graph. Okay? All right, so that's reading the graph. Okay? Now, calculating stuff off the graph. What if I were to give you this position versus time graph? Okay, so do we have a single linear function on this graph? Okay. It's only doing one thing. The line is just diagonal, doesn't do anything else. Okay, so if I gave you this graph, here's probably one of the things I would ask you. What's the velocity of this object? Give you a hint. This question would be out of 1 mark.
3.5 meters per second.
3.5 meters per second. How do we know that on this graph, the slope, right, because this is y equals m times x plus b, okay? How do we know that the slope on this graph represents the velocity of the object?
It's the amount the object changes over time, and time is x.
Right. Okay. I mean, if we manipulate this formula to solve for slope, okay, so if we manipulate this for m, it'll be y minus b over x. Okay. On my y-axis is position. On my x-axis is time. So when I do this, am I really just doing this? Right? Would would the y-intercept be my initial position on this graph? Where the object is at time 0. Okay, so that would be my initial position. Okay, y is any other position along that line. Okay, so I would define that as my final position. And if I divide that by the time, I'm calculating displacement over time, which calculates velocity. Okay, again, I don't have to memorize that. I just analyze it from the graph. Okay? On every graph, the slope represents something different. Okay? We're going to learn that today when we look at velocity versus time graphs. The slope on that graph represents something else. Okay? But I can analyze it and figure out what it is. Okay? Does any of this ring a bell? Okay. All right, here's something else I might ask. What will be the position of the object after 25 seconds? Okay, so let's say this. Calculate that for me. What's the position of the object after 25 seconds? So I already know what M is. I already know what B is. Probably not being asked to solve for either one of those. Okay? If they want me to solve for position, am I solving for Y or X? Y. Because position is on the Y axis. They're asking me to solve for a Y value, and what did they give me? 25 seconds. Which axis is seconds on? The x-axis. So they gave me x. They want me to find what is y when x is 25. Okay, so that means I can just plug into this formula. It's already set up to solve for y. I don't have to do anything except put 25 in for
3.5.
yeah, well, not in for 3.5, but in for x. Right. Yeah. So if I do that, then y, my position, is going to be 3.5 meters per second times 25 seconds plus negative 2.5 meters. Okay, that should get me my final position here. Okay, so 85 meters, positive 85 meters, okay, would be my position after 25 seconds. Okay, did I ring a bell from last year? If you were in my science 10 class, I definitely asked you to do that. Okay, all right, here's the other thing I might ask. How long to reach a position of, I should put positive, 168 meters. Give you a minute on that one. All right. What am I being asked to solve for? Y or X?
X.
Being asked to solve for X. How long? Time is on the X-axis. All right, so I've got to manipulate now to solve for X. All right, so X is going to equal Y minus B divided by M. Okay, they gave me the Y value, positive 168. Okay, I know B is negative 2.5, so minus negative 2.5. okay, divided by m, which is positive 3.5. All right, so that's going to take 48 seconds, actually 49 seconds. Okay, if you didn't get that, make a note of how I did this. I calculated what the top was before I divided it by the bottom. Okay, and you have to do that, right? If you just type the whole thing in, then it divided negative 2.5 by 3.5 and then subtracted that from 168, which is not the same thing. Okay, easy mistake to make on the calculator. All right, is that ringing a bell? Okay, this is either good news or bad news for you, depending on whether this rings a bell. This is tomorrow's lab. Position versus time graph, linear functions. Okay, what's the slope? What does it represent? Okay, how do I calculate how far it will go in a certain amount of time? How do I calculate how long it'll take to reach a certain position? That's tomorrow's lab. Okay, we've done stuff like that before, so that lab should be fairly familiar territory for you. Okay. All right, so slope calculations. Okay, remember that when we calculate the slope, okay, we are more than likely going to be doing this: y equals m times x plus b. Okay, that doesn't mean that this formula, which is essentially rise over run, is not valid. Okay, it is totally valid. It's just already taken care of with this formula. Okay, if I manipulate this formula for m, I'm going y minus b over x. Well, that's y, that's b, and that's x. Am I still doing rise over run when I do that? Okay, it's the same thing. Okay, we just like y equals mx plus b better because when we have a linear function, we can use it to get more stuff. Okay. All right. So the thing to remember here, guys, is that on every graph, setting this up can allow you to calculate or figure out what does the slope represent. Okay, because on every graph, the slope represents something different. What you have to do is look at what's on each axis and figure out what it represents. Okay, so let's say, for example, I gave you a graph that looked like this. Okay, so I've got a graph where on the y-axis I've got the value of shares. Okay, so if you own stock in Disney, your graph would look like this. Okay, so the value of your shares is clearly declining over the space of several weeks. Okay, so what would my slope represent on this if I'm looking at dollars on the y-axis and weeks on the x-axis? My slope would be dollars per week. Okay, I'd be able to calculate how much money I was losing, okay, at a rate of per week, okay, with this graph. That's what the slope would represent. Okay, everybody all right with that? That way we don't have to memorize, oh, the slope on this graph is this, and the slope on this graph is this, okay, because you're going to get confused at some point and get it wrong. Okay? Better to analyze each and every graph. Okay, so let's say I give you a position versus time graph that looks like this one. Okay, one of the first things I can ask you is, what's going on in part A? What's the object doing in part A?
Moving forward at a constant rate.
Awesome, moving forward at a constant rate. Okay, I know it's constant because it's a diagonal line. It goes up the same amount of every time it goes over. Okay, what's going on in part B?
It's not moving?
It's not moving, okay? Because I'm stuck at a position of 6 meters for, 4 seconds. Okay, it's not moving. What's going on in part C?
The object is moving backwards at a constant rate.
Moving backwards at a constant rate. Still a diagonal line, okay? Just now it's sloped downwards, which means my position is becoming more negative every second, but it's doing that at a constant rate, moving backwards at a constant rate. Okay, obviously in D, we've already covered that. What's it doing in D?
It's not moving.
Not moving. Okay. E and F are both moving forwards. Which one's faster, E or F? E, how do you know?
Because it takes less time to go long distance.
Yeah, it's steeper, right? It takes less time to go a longer distance. It's steeper. And we know slope represents velocity on this graph. Steeper the line, faster the object is going. Okay? These are the kind of interpretation things you could be asked. All right, some calculation stuff. What is the total displacement of this object over the entire 18-second trip?
0.
0. How do we know? How do we know that? Brad, how did you figure that out?
Just like it ended up back at 0 at the beginning.
Yeah, exactly. Its initial position was 0. Its final position was also 0. Okay, final position minus initial position is how you get displacement. 0 minus 0 is still 0. Okay, all right. What's the average velocity over the entire 18 seconds?
0.
Also 0. Okay, velocity is displacement divided by time. If I didn't displace myself, I don't have any measurable velocity either. Okay, those are the two easier ones. Now I want you to calculate the total distance traveled. This one's going to take you a few minutes. Okay, I want the total distance traveled. The hint I'll give you, you got to do it piece by piece. All right, so does distance care whether I go forward or backward? Distance just cares how far I go, which means I've got to figure out the change in position on each section of the graph and then do what with all those numbers? I'm looking for a total. What do I usually do? Add them. Yeah. Okay, so in this first one here, I go from 0 to 6 meters. How far is that? 6 meters, last time I checked. Okay, so that part's 6 meters. And we said here we were stopped, so we don't go anywhere during that point in time. From here, we go from +6 to -10. That's 16 meters. Remember, direction doesn't matter here, okay, because I'm trying to calculate distance. Here, we know we don't go anywhere, okay, so that's 0 meters. And then we go from here all the way to here. It doesn't matter that I do that at different speeds. I just need to know how far it is from here to here, and that's going to be another 10 meters. Okay, so 10 plus 16 is 26, plus 6 is 32 meters. Okay, that's my total distance traveled. Right, is that something I could ask you to do on a quiz or a test?
Yeah.
Definitely. Okay, next question. What's my average speed over the whole trip? Spoiler alert, you've done the bulk of the work for this already. Haven't given you guys your formula sheets yet, have I? Okay. All right, so just in case we've forgotten, speed equals distance divided by time. Do I already know the distance? Just calculated, it's 32 meters. Do I know the time? 18 seconds. Okay, so all I have to do is go 32 divided by 18, should get like 1.8 or 9, something like that. 1.72?
1.7 repeating.
1.7 repeating, okay, so 1.8.
Maybe a tweak, but that looks like it's
Okay, everybody all right with that? Okay. All right, that we're gonna skip. Okay, now, this is our, another position versus time graph. But what is this object doing? What's it doing from, let's say, here to there? It's accelerating, okay? We know that because every time interval, it goes further, okay? Just like we were talking about before. Okay, it goes further every time interval. The only way it can go further in one time interval than it went in the others if it goes faster. Okay, in this case, it's going faster and faster and faster. All right. What's it doing in this part of the graph? From here to there.
Decelerating.
Yeah, it's slowing down. Okay? In fact, it actually comes to a stop for an instant. Okay? It comes to a stop for an instant before, what is this part?
Accelerating backwards.
Accelerating backwards. Okay, that line, did it get steeper and steeper and steeper going this way? Is it the mirror image of the other side? Okay, and then what's it doing here? Keeping in mind that the line is getting flatter and flatter and flatter.
Decelerating backwards.
Yeah, it's slowing down again. Okay, and in fact, it comes to a stop. What is this a graph of?
Something being thrown in the air.
Yeah, something being thrown in the air. Okay, so the first part of this graph, part A, is me throwing the marker. Okay, in that part, it's accelerating because when it's in my hand down here, it's not moving. Okay, and I throw it upwards. Okay, I make it go faster and faster and faster. As soon as it leaves my hand, what's starting to happen to it? What's acting on it now?
Gravity.
Gravity. Okay, gravity is trying to pull it back. Okay, because what goes up must come down. That's this part of the graph right here. This is the what goes up must come down part of the graph. It's slowing down, slowing down, slowing down. And when it gets to its maximum height, it stops for an instant before it does the exact opposite. That's why these are mirror images of each other as it falls back down to my hand. Okay? The acceleration in both parts of this graph on either side of B are the same. They're 9.81 meters per second squared. Okay? That object is accelerating at 9.81 meters per second squared down during both its upward and downward flight. Okay? The last part of that graph is me catching the marker and slowing it to a stop. Okay? I would never ask that on a test. I would never give you a graph and go, what's this? Okay? And you'd have to, like if I gave you that and you'd have to, the correct answer would be a marker being thrown up in the air. That would be totally unfair. Okay? But could I ask you to describe every section? Absolutely. Okay, so just as kind of a quick aside here, we know that the slope of the line on a position time graph tells us the velocity of the object. Okay, that's part of the reason we know when a curve is going like this, the object is going faster. Okay, it's accelerating because the line is getting steeper, steeper, and steeper. Okay, everyone okay with that idea? Okay, so I'm going to tell you right now the only thing I understood in university math, university calculus in fact, okay, and it was unfortunately the very first day. And I didn't understand anything after that. Okay? I passed the class by memorizing the examples in the textbook and writing them down on the final exam and getting part marks for method. Luckily, I was in a class full of people who were even less good at math than me. Okay? Because it was graded on the curve, my level of stupidity was less than everyone else's, so I did okay. So, on this graph, okay, to a mathematician, a curve looks like what you see when you look at a low-resolution picture or watch a low-resolution video on like YouTube or something like that. What can you see if it's low resolution? What are all the little squares called? Pixels. Okay? Well, to a mathematician, this is not a curve. It's an infinitely large number of infinitely small straight lines that get steeper and steeper and steeper. Okay? So when they see that, they see a pixelated picture that shows a whole bunch of lines getting ever steeper. Okay? On this part of the graph, okay, they see an infinite number of lines that are, getting less and less or more and more flat. Okay? And here more and more steep, and here more and more flat. Okay? That's what they see. That's what's going on in any curved part of a graph. The slope of the line is changing, either getting steeper or getting flatter. Okay? All right. Okay, we've done one like this. I want you to try this now without any guidance from me. Okay, you have a position versus time graph. You have the equation for the line. Okay, I want you to calculate those two things. Okay, so once again, this is just like your lab is going to be tomorrow, right? You're going to collect data and you're going to get a nice straight line like this tomorrow, okay? And you're going to be asked to do very similar things with it. All right, so I've got a position versus time graph. This position versus time graph is showing me an object traveling at a constant velocity, okay? The best fit line is diagonal. And I know the slope of that best fit line is 3.85 meters per second. Okay? Now, they want me to calculate the position of the object after 1 minute. That means they want me to calculate y. Okay, so that's going to mean m times 1 minute. That's the trick in this one. You got to have it in seconds if your velocity is in seconds. Okay, plus my initial position, negative 0.801. All right, so 3.85, not 2.85 times 60 plus negative 0.801. Okay, so we're looking at a position of 230 meters. We have only one significant digit. That's terrible. So we would say 2 times 10 to the 2 meters on that one. Okay, and then for number 2, how long it'll take to reach a position of 150 meters means taking y equals m times x plus b and solving for x. So that'll be y minus b divided by m. Okay, so that'll be 150 minus negative 0.801, okay, divided by 3.85. Okay, so we're looking at 39. We only have, so we do have 3 significant digits on that one, so we'd say 39.2 seconds. Okay? Everybody all right with that? Okay, hopefully that's feeling a little bit familiar, okay, from last year. Okay, if I'm looking at this position versus time graph here, at time 0, which object is further ahead? Run 1 or run 2? Okay, well, run 1 is the blue line. Looks to me like the blue dots start further up the y-axis than the red dots. Agreed? Okay, so run 1 had a head start. Okay? I've often asked that as like a multiple choice question. Okay? What is true at time 0? A and B are both at the same position. A is ahead of B. B is ahead of A. A is moving faster than B. Incidentally, if I said A is moving faster than B, would you be able to tell that at time 0? You wouldn't, because nothing's happened yet. All you know is where they are. You don't know how fast they're going until you're at a time other than 0. Tricky question. That might be foreshadowing. I think that's what it's called right in English when you tell the future. Okay. All right. Which object's faster? 1 or 2? Okay. Line steeper for 2, has a greater slope. Okay. Plus we can see that numerically here. Run 2's slope is 0.38, where run 1's slope is 0.26. All right. Those are, again, interpretation type questions that you could get. Okay, I think we got time for this. So let's say velocity of each cart. I'm going to keep question 1 the way it is. The position of cart 3 after 12 seconds, and how long it will take cart 1 to reach a position of 50 meters. Okay, we've already done these calculations, it's just a different graph. Okay, so I want the velocity of each cart for part 1. Okay, and then number 2, position of cart 3 after 12 seconds, and how long it will take cart 1 to reach a position of 50 meters. Okay, so on a position versus time graph, the slope tells me how quickly I change my position as a function of time. Agreed? The other way of saying that is the object's velocity. So the slope is the velocity. So all I have to do for number 1 is say cart 1 is 1.38 meters per second, cart 2 is 2.01 meters per second, and 3.39 meters per second for cart 3. Okay, all of them positive because they're in a forward direction. Okay, that's all I have to do for question number 1. Okay, in question number 2, we want the position of cart 3 after 12 seconds. So that means we're dealing with this equation, and x is how much? What value do I put in for x? 12 seconds, that's what they told me there. Okay, so 3.39 times 12 plus 0.0381. All right, so we're looking at 41 seconds. Sorry, 41 meters, sorry. Positive 41 meters. Okay, and then for question number 3, how long for cart 1 to reach a position of 50 meters? Okay, so x equals y minus b over m, right? For cart 1, right, that's going to be 50 minus 9.52 times 10 to the minus 3, that's what that means, okay? And then divide that by 1.38. Okay, so we're looking at 36 seconds for that one there. Okay. All right. I'm going to give you about a 5-minute break here, and then we're going to talk about velocity versus time graphs. Okay. Okay, something that at least one member of your group is going to need on their phone for tomorrow, okay, because we're doing our graphing lab tomorrow, is the Spark View app, spelt that way. Okay, so you need to go into the App Store and you need to find that app, okay, and put it on your phone. It's free, okay, works really good. This is going to sound really snobby, and it is, but it only works really good on iOS. Okay, we've tried the Android version a bunch of times, and for some reason it's not happy. Okay, it works fine if you have it in Chrome OS. You can hook it up to a Chromebook and it'll work, but it just doesn't work on Android for whatever reason. So just make sure one person in your group has an iPhone, which statistically shouldn't be too hard, since that seems to be what most people have. Okay, so at least one person in your group needs to have an iPhone with that app installed on it for tomorrow, because that will connect to our carts, okay, and our carts will take data 20 times per second while they move, okay, and send that to your phone, and then we will use that to build our position versus time graphs tomorrow. Okay. All right, now we got to talk quickly about velocity versus time graphs. So what can I read directly off of velocity versus time graph?
Velocity and time.
Velocity and time. I can tell how fast and in what direction an object is going just by looking at the graph. From that, I can also infer a few things, just like I could on the position versus time graph. I can tell whether that object is traveling at a constant velocity, which direction it's doing that, and I can determine whether it is accelerating and which direction it is accelerating, okay, based on the shape of the graph. All right, now, I can also calculate a few things from the velocity versus time graph. I can calculate average velocity, total displacement, total distance traveled, and acceleration. That's something I couldn't calculate on my position versus time graph. Okay, so I can calculate a few things there. Now, these two graphs right here, one is a position versus time graph, the other is a velocity versus time graph. Are they showing the same thing or different things? Okay, the position versus time graph is the one on the left. If it's showing a diagonal line, what does that object do?
I think they're showing the same. It's like a constant velocity or speed.
Exactly. It is showing an object traveling at a constant velocity. Not just any object, exactly the same object, in fact. Okay? This isn't just one of them is showing an object traveling at a constant velocity, the other is showing a constant velocity. They're showing the same velocity, thus the same object. All right? So here's how we can prove that. Does the slope of this line tell me the velocity of the object if that's a position versus time graph? It does. Okay, so I should be able then to calculate what m is if I know y, if I know b, and I know x. And I actually do know all of those things because I can read them off the graph. I'm going to use this last point as y, 1400. Okay, I'm going to use this point as b, okay, so minus 100. And then x goes from 0 to 5 seconds divided by 5. Right? So 1300 divided by 5 should be 260 meters per second. Is that what this graph is showing? Right? If this is a velocity versus time graph, this would be 250, so that's about 260, and it's showing it not changing. So yeah, in fact, they are showing exactly the same object. Now, on this graph, on the position versus time graph, was it easy to figure out what the displacement is? In fact, I kind of did it already, didn't I? Right, I went final position minus initial position. So my displacement was 1,300 meters. Could I calculate that from the other graph? Okay. So I used final position minus initial position on this graph. I can't do that here because this graph doesn't show position. But this graph does show velocity. And time. So if I manipulate that formula to solve for D, it would look like this, right? Average velocity times time equals displacement. According to this graph, the velocity is constant at 260 meters per second. Does that mean the average velocity is also 260? It does, okay? And the time is 5 seconds. So that's what I got on the other graph. Okay? Now, in Science 10, you were probably taught, calculate the area under the line and you'll have the displacement. Right? And you find the area of all the shapes and you'll have the displacement. Okay? Which is totally fine. Okay? We can do that. But what we want to do is we also want to understand where that comes from and why that works. Okay? When I calculate the area underneath this line, this is what I'm doing. I'm taking average velocity and multiplying it by time. I'm just using v equals d over t. Now, what if the graph looked like this instead? Now, instead of a rectangle, I have a triangle, right? Okay, if I want to calculate the area between underneath the line like this, now it's a triangle. How do I calculate the area of a triangle?
Base times height divided by 2.
Base times height divided by 2. Okay, what's on the base of my graph?
Time.
Time. Whoop. Okay. What's the height of my graph? Velocity, right? Okay, now in this graph, this object is accelerating. Its velocity is changing from this value to this value. Would its average be halfway between those two? Or the height of the triangle divided by 2? Okay? That's calculating the average velocity. It doesn't change at all. Whether it's a rectangle or a triangle, I'm still multiplying time by average velocity. Okay? That's why that works. Okay? All right, does that ring a bell from Science 10? If you took my Science 10 class, you've actually seen this slide before because I used it in Science 10 as well. Okay, so we got a velocity versus time graph. What's the object doing, or what's the runner, because this is a runner. What's the runner doing in the first 5 seconds or so?
Accelerating.
Accelerating. Velocity's going up from just barely above 0 to pretty much 8. Okay, and then what?
Running at a constant speed.
Running at a constant speed for the next 5 seconds or so. And then?
He decelerates.
Decelerate. In fact, they come to a
Stop.
stop because their velocity ends up being 0 at the end. Okay, this is exactly what any runner's graph would look like, okay, for a sprint. Okay, there'd be the part where you accelerate, where you're pulling really hard out of the blocks. Okay, and then as you accelerate, eventually you reach your top speed, and it doesn't matter how hard you push, you cannot physically run any faster than that. Okay, and you run at that speed for the rest of the race until you cross the finish line, and then you slow down and come to a stop. Okay, hopefully in a controlled manner, not by falling. Okay, everyone follow me there? Now, that's generally what every runner's graph looks like, but if you are an elite level sprinter, your coach might actually analyze your graph and look at where you need to improve your running in order to run faster. Okay? This person is not particularly fast. Okay? 8 meters per second is even possible for an old guy like me probably. Okay? Usain Bolt runs at over 17 meters per second, or did. Now he's an old man too. Okay? But in his prime, he could run at 17 meters per second at his top speed. What made him great was that he was a terrible accelerator. Okay, coming out of the blocks, I mean, the guy was 6'7". He had to basically unfold himself like a lawn chair, okay, when he got out of the blocks. And when you're 6'7", you're kind of long. So he didn't accelerate really well. Plus, he wasn't built like powerfully. Okay, he was tall and lanky. Okay, but once he got to his top speed, it didn't matter. Okay? It didn't matter how quickly everybody else got out of the blocks. He was going to run you down. Okay? Especially in the 200 meter, where he could run at 17 meters per second for 18, well, not 18 seconds, but probably about 12 seconds. Okay, that sort of makes sense? Okay, a coach can analyze your graph and say, you're great at accelerating, but we got to work on your top speed, and we'll focus less on power and more on speed, okay? Versus, you know, Usain Bolt's coach, well, he obviously had, you know, a freak of nature, okay? But, you know, he should have worked a little bit more on his acceleration. And in his final races, you actually see he does do better, okay? That sort of makes sense? That's kind of an application of this stuff. If you ever go into, you know, coaching, kinesiology, stuff like that, okay? There's people that make a lot of money in life, okay? Just kind of fine-tuning high-end athletes so that they can be the best they can be. Okay, so on a velocity versus time graph, obviously we can read the velocity of the object. It's the vertical value of a point on the graph, okay? We can calculate the displacement by finding the area under the line. That's average velocity times time, okay? What does the slope represent on a velocity time graph?
Acceleration.
It represents the acceleration. Okay, so think about this. I've got a velocity versus time graph. It looks like this. I've got meters per second on the y. I've got seconds on the x. Okay? When this graph goes up, I'm seeing an increase in my velocity in meters per second. Per second. Okay, so when I calculate the slope, and I go y minus b divided by x, what I'm doing is dividing meters per second by seconds and getting meters per second, or meters per second squared, the units for acceleration. It tells me the rate at which I change my velocity, okay, in meters per second. All right? Everyone okay with that? Okay, that's another one of those things. We don't want to memorize that. We can analyze that from the graph. Okay? All right, those were all the things you were asked to do with a velocity versus time graph in Science 10. Okay? We haven't really done anything new today. Okay? It's just a review of that stuff, because you're actually not going to be asked to do anything different with those two graphs than you were in Science 10. Okay? There really isn't anything else we can do with those two graphs. Okay, we've got a velocity versus time graph here, okay? Five different objects on it, okay? Which one is the fastest accelerator?
Orange?
Yep, the orange one, run 5, okay? How do we know that?
Because they travel the most distance in the shortest amount of time based on their like slope or angle up and down.
Okay, they have the greatest slope. We don't necessarily know about the distance, it's likely, okay, but we don't actually see the distance on this graph. What we see is velocity, sorry, it's blocked out over here, okay, in meters per second. We see the greatest or quickest change in velocity for that particular object, okay? So then obviously that would make run 1 the slowest accelerator, okay? Is it possible that all of these objects might actually go the same distance?
Yes.
Yes, it is. Okay? I mean, we would calculate their displacements in the same way. We'd calculate the area under the line. For this orange one, that would actually be, okay, a rectangle and a triangle, okay, looking kind of like that, right? For the green one, right, we would just have that triangle, right? And then for our yellow one, okay, the triangle is shallow, okay, and so on and so on and so on. If we just look at those, and actually I shouldn't have drawn that one where it was, okay, the areas of those lines might actually be very similar. Right? They might actually have traveled the same distance because they didn't travel for the same amount of time. Okay? Run 1 is much slower. It travels for much longer. It may actually end up going the same distance as run 1, or run 5, sorry. Okay. All right. So that would be the kind of thing I might ask you as a multiple choice question, an inference or an interpretation of the graph kind of question. Okay. Which one of these cars starts out moving in a positive direction? That's a trickier one. 4 out of the 5 are actually moving in a negative direction at time 0. You can't tell that by looking at their lines. Well, you sort of can. Which one is the only one moving in a forward direction at time 0? Okay, is your velocity at time 0 your initial velocity? Okay. What part of this equation on this graph would represent my initial velocity?
B.
B. B is the y-intercept. And on this graph, that is how fast the object is going at time 0. Okay? The only one of these lines that has a positive value for B is run 5. Okay? This is another thing I could ask you. Okay? And see whether you can tell what each part of y equals mx plus b represents for this graph. Okay? On our last graph, b was the initial position. On this graph, b is the initial velocity. B is always the initial y. Okay? Whatever's on the y-axis, b is the initial value of it. Okay? So it could be pi, initial position. It could be vi, initial velocity. It could be initial value of shares. It could be initial mass. Okay? If you were, somebody who was going to start working out and you wanted to put on, some mass. Okay? Vi or the V could be your initial mass, and then you graph it from there. Okay, all depends.
Would red also be positive? Because this is 0.03.
Oh, it is. Sorry. You are absolutely right. Sorry, I thought I saw a negative there, but I am wrong. And you are right. Yes, it is very, very small, but you are right. Okay? Sorry, there are 2 on there. My bad. Okay. All right. Okay, rather than do this part, here's what I want you to do for that graph. I'll try and make it a little bit bigger. Okay, I would like you to calculate for me the total displacement of the snowmobile. From this velocity versus time there. All right, so if I want to calculate the total displacement, I need the area under the line, or the average velocity times the time for each section of the graph. That includes this box here. This is the one that people forget. Okay, and of course this triangle up top. All right, so I've got this triangle here that is 20 on the base and 40 high. Okay, so 20 times 40, 800. Okay, divided by 2 is 400. Okay, I'm doing mental math. Check me if I'm wrong. Okay, and then I've got from 20 to 60, that's 40. 40 times 40, 1600. Okay, meters, am I wrong? My mental math, okay, I really shouldn't do mental math, but I was doing it. Okay, and then I've got this triangle here that's 10 on the base and 20 high. 10 times 20 is 200, divided by 2 is 100 meters, okay, which should give me 1,700, 2,100 meters. Okay, and that would be positive because it's the total displacement. Okay, it would also be 2,100 meters if it was the total distance. Okay, everybody all right with that? Tomorrow, what do you have besides the lab? Quiz, practice quiz. We'll post at 3:20 today, okay? Or shortly thereafter when we will have set for 3:20, but sometimes it's a minute late, okay? So that'll post with a solutions video, okay? So you can try the questions, then watch the solution video, see if you did it right, okay? Spoiler alert, it's one multi-part B equals D over T question and one position versus time graph question. Okay, and your quiz tomorrow will be very similar to that. Okay.